So I'm going to give you some sets. You're going to tell me if these sets are the same sets or they are just the same size. All right. So 2 scenarios. Scenario A, we have a class register for period 1, Ama, Kofi, and Ya. And in period 2, Ya, Ama, and Kofi. Then in scenario B, we have science club made up of Ama, Kofi, and Ya. And the drama club, we have Ben, Rose, and Kwame. So in scenario A, you're going to answer, are they the same? Period 1, Ama, Kofi, Ya. Period 2, Ya, Ama, Kofi. For me, I'm seeing Ama, Kofi, Ya, and I'm seeing Ama, Kofi, Ya. So are they the same? Yes, because both lists have the same 3 students, just that what? The order differs. So in set theory, these are the same set. That's what we call equal set. Order doesn't matter. Scenario B, are they the same? So in the science club, I see Ama, Kofi, Ya. In the drama club, I see Ben, Rose, Kwame. I don't see Ama, nor Kofi, nor Ya, right? But then I see 3 students here, and I equally see 3 students here. So here we have both clubs having 3 members. Completely different people, but 3 members. So they have the same size, but not the same elements, not the same set. So these are what we refer to as equivalent, not equal, equivalent, all right? So in this lesson, we are going to learn how to tell the difference between equivalent sets and equal sets and use the correct mathematical notations for them. Let's begin with equal sets. Let's define. So 2 sets are said to be equal if they contain exactly the same element. Emphasis on what? Exactly the same element. Remember, the order doesn't matter. Repetition does not matter. All we're looking at is if elements in A are the same elements in B. And we use the equal sign to denote this. So the test here is, does every element of A appear in B? And does every element of B appear in A? Let's look at some examples. So A equals set of what? 1, 2, 3. B, 3, 2, 1. Are they equal? Ask yourself, is every element in A in B, and does every element in B can be found in A? So we have 1, 2, 3. And in B, I see 1, 2, 3. Just as it has been ordered differently, right? But I see the same element. Therefore, A equals B. What about this one? So X equals red, blue, green. Y equals blue, green, red. So red, red, blue, blue, green, green, red, red, blue, blue, green, green. So each element in X can be found in Y, and each element in Y can be found in X. Ergo, we have what? Equal sets. And what about this one? Yeah, I know the change in color is tipping you off, but still, we're going to do it together. So we see P equals 2, 4, 6, 8, and Q equals 2, 4, 8, 10. So let's check. 2, 2, 4, 4, 6. There's no 6. But 8, 8. Then if you are doing it from here and here, we have 2, 2, 4, 4, 8, 8, 10. No 10. So we can see that what? Every element in P can be found in Q. Nor can every element in Q be found in P. Therefore, not equal. Let's look at the last one. C equals AABC and D equals ABC. Remember, repetition doesn't matter. A is still A. Okay, so we have ABC here and we have ABC here. So they are equal. So let's look at why order and repetition don't really matter in equal sets. Remember, a set is defined by membership, not arrangement. So the only question that matters here is this element in or out? This is why order doesn't matter. So you think of the set as a bag, not a queue. So in the bag, it doesn't matter which item is first. You can have 1, 2, 3 in there. You can have 3, 2, 1 in there. But they're the same bag of members, okay? So you would find that exactly the same items can be found in what? Either bags. Now, why repetition doesn't matter? A set is tracking whether an element is a member, not how many times it appears. So if you say apple, apple, banana, it doesn't give you 2 apples in a set. You have just what? Apple. So apple is simply a member. So remember, when we are testing for equality, what we are doing is that we are checking that every element of A is in B and every element of B is in A. If both conditions hold, then A equal B. Okay, so this is the formal definition of equality used in math. For now, remember, say equivalent set. So two sets are said to be equivalent if they have the same number of elements. So even if the elements themselves are completely different, but they have the same number of elements, then we say what? They are equivalent. And we use what? We use this to denote what? The equivalence. We don't use equal to here. All right. So the test is what? Is the cardinality, right? The number of elements in A equal the number of elements in B. If yes, they are equivalent. Let's try. So we have A equals ABC. B equals 1, 2, 3. So number of elements here, 1, 2, 3. Number of elements here, 1, 2, 3. So since the number of elements are both 3, then what? A is equivalent to what? B. All right. A is equivalent to B. But remember, A is not equal to B because here I'm seeing letters and I'm seeing what? Numbers. Different. Okay. So different elements. Therefore, they are not equal. But their sizes are the same. And that's what makes them what? Equivalent. What about this one? X equals cat dog, Y equals 5, 10. Number of elements here, 2. Number of elements here, 2. Therefore, what? They are equivalent. Let's try the third one. So P equals vowels in math. What the vowel in math? Just A. This is not mathematics, just looking at maths. So A. Then our set Q is what? 7. So number of elements here is 1. Number of elements here, 1. What type of set is this? They both have just one element. That's singleton set. So they are both singleton sets. And for that, what? They are equivalent. Let's try the last one. C equals 1, 2, 3, 4. D equals ABC. Number of elements here? 4. Exactly. Number of elements here? 3. So their sizes are not the same. Therefore, they are not equivalent. Do we get that? So they have a different cardinality. So they are not equivalent. All right. So the critical relationship is what? Equal versus equivalent. Every equal set is equivalent, but not every equivalent set is equal. This is very important, okay? So why? Because equality is stronger than equivalence. Let's look at the features here. So, meaning equal sets, they have exactly the same element, right? But for equivalent sets, they have the same number of elements. So here, the items, the members, they are the same. Here, the sizes are the same. Does order matter? No. Order does not matter to both of them. Let's take an example. So for equal sets, we have 1, 2, 3. Then here, 3, 2, 1. It's 1, 2, 3. Remember, order does not matter. Therefore, equivalent set A, B, C, 1, 2, 3. Size 3, size 3. Same elements inside, right? Size 3 and size 3. So let's look at this question. Is the other also true? Is equal always equivalent? Yes. Look at this. What's the size? 1, 2, 3, 1, 2, 3. So they both have what? 3, 3, and they are equivalent. Now, are the elements inside the same? 1, 2, 3, 1, 2, 3. So you see, equal, they are the same. So equality always will triumph over equivalence. Equality is stronger. Because think about it. If these two sets are equal, equal means they have the what? The same members. So if you have the same members here and you have the same members there, then automatically the sizes of both what? Sets will be the same. And that is the reason why equal is always equivalent. But equivalence is not necessarily equal. Yeah, the sizes are the same. That's what makes it equivalent. But the members in here, you are letters, alphabet, and we are numbers. So we are not the same element, even though we have the same size. Is that understood, please? It's just like saying all squares are rectangles, but not all rectangles are squares. Remember that rectangles, opposite sides are what? Opposite lengths are equal. Then for square, all 4 lengths are equal. But technically, opposite what? Are equal. So all squares are rectangles, but not all rectangles are squares, because rectangles don't have all 4 sides being the same. This is pretty easy, right? Okay, so let's visualize. Let's visualize the relationship between equal and equivalent sets. So we are going to think of nested circles, okay? Every equal set is going to sit inside the word of what? Equivalent set. So this equivalent set, remember, they have the same size, not the same members. Example, A, B, C, 1, 2, 3. Same size, but then different elements inside. Then for equal sets, they have the same elements, okay? A equal B, example, 1, 2, 3, 3, 1, 2. So the elements inside, they are the what? They are the same. And then their sizes are the same as well. So let's look at these key rules. If A equal B, if A 1, 2, 3 equal B 1, 2, 3, then the sizes 3, 3 size would always be what? Equal, and therefore the A would always be what? Equivalent to B. So remember, equal sets, they are sharing the same element. Equivalent sets, they are sharing the same cardinality or the same size.